Okay, roll camera.
Roll camera's on.
And action.
Hi, I'm Suzette for Algor Incorporated. Today's episode is titled Escape from the Past or Solving the Case of the Buckled Bar. Engineering began in the ancient world. Among the many creations of ancient engineering are three huge pyramids at Giza, Egypt, known as the seventh wonder of the ancient world. Their method of construction is today shrouded in mystery. Engineering methods advanced rapidly through the millennium. Culminating with today's method of computerized finite element stress analysis. Now, as we stand on the threshold of the 21st century, it's time to escape from the past. Let's consider this aluminum bar. We will run an experiment to see if Algor's Accupak VE virtual engineering software can predict if the bar will hold up or fold up when a weight is placed on one end of the bar. We will use this mechanism, the universal Algor testing machine. The bar is hinged at each end, by this hinge here at the bottom, and by this hinge in the carrier at the top. Note how the carrier, which can hold a variety of weights, slides along these vertical rods. In this experiment, we will have a weight on top of the bar. This weight will be held in place with this electromagnet. When we release the weight, it may cause the bar to buckle out to the side. The bar would impact this 2x4, which will serve as the floor. Let's now model the experiment using Algor's Accupak VE to simulate this event and predict the maximum weight the bar can handle without buckling. Our plan is to see what will actually happen through animation on the computer screen. This what you see is what you get scenario is what we call virtual engineering. Then we will do the live experiment and compare the results with those predicted by the virtual simulation. We are starting out with roadmaps, Algor's Java-based, easy-to-use human interface. Now we select SuperDraw 3. SuperDraw 3's user-friendly features let us easily and quickly build this model. We simulate the effect of the hinges or joints using these small wedge elements. Using the FEA Add menu, we fix these nodes on the wedge and thus create a hinge. We constrain the top hinge to move along a vertical line, just like in the physical experiment. We do not know in advance which points on the bar will contact the floor. Therefore, in this case, as in many impact problems, the use of contact elements is not desired. What is needed is the ability for the points on the bar to contact the floor automatically. All the user has to do is put in the location of the floor. The software will automatically predict which parts of the bar will actually make contact with the floor. We will do two runs, one with 16 pounds of weight and one with 20 pounds of weight. Using Algor's new monitoring capability, we can see events unfolding on our computer screen as results are computed. After each run, we make a computer animation from the results. Here is the result of the run with 16 pounds in 1/4 time slow motion. Buckling is not predicted. And here is the results of the run with 20 pounds. It predicts several things. First, the bar is indeed buckling under the 20-pound weight. Second, a very large deformation has occurred. Third, the bar did contact the floor, which constrained it and forced it into its final shape. Let's further examine the significance of the floor. Without it, we still get buckling, but it is nothing like the correct simulation. Finally, modeling the removal of all the weight, we obtain the permanently deformed shape. Measuring the distance between the two ends with SuperView, we obtain 16.5 inches separating them in the permanently deformed condition. Let's go back to the experiment and see how well we predicted the event. First, we will use a 16-pound weight. Pressing the button releases the weight. Note that the bar supports the weight as predicted. Now the same test with the 20 pounds of weight. Again, pressing the button. Note that in fact, the column has indeed buckled as predicted. We do have a very large deformation. And the bar has contacted the floor, forcing it into the final shape. Let's do an instant replay in slow motion. As you can see, the Accupak event simulation and the actual event match closely. Let's remove the bar from the apparatus so we can measure the permanent deformation. Observe how closely Accupak VE predicted the permanent deformation. Predicting the event you just saw with the finite element system could be a formidable challenge. One of the more challenging aspects is predicting the contact and the subsequent separation between the bar and the floor. With Accupak VE, however, all we had to do was build the model and specify the location of the floor. There was no need to put in special contact elements. Everything was automatic. The Accupak VE event simulation, the actual event, the case solved. Virtual engineering and automatic contact from Algor for engineering in the 21st century.
We are showing how Algor software predicts fluid flow interacting with a structure. We will use this 12-volt computer chip fan to show how Algor can optimize its design. Notice the rib that houses the wires is wider than the other two ribs. Those are thinner because they thought it might be a better design. Let's begin the experiment. The fan and the housing are rigid. The fan is rotating at 300 RPM. We are using smoke to dramatize the airflow. Notice the flow pattern near the narrow ribs. Now, let's go to the computer to see if Algor can make the design better. The finite element model of the blade and housing was made in Algor SuperDraw. The real fan was photographed with a digital camera to produce a bitmap. The engineer used a tracing function in SuperDraw to construct the blade geometry of the model. SuperDraw needs only a few mouse clicks to create the mesh around the blades. Next, a surface mesh of the remaining volume was automatically generated and fitted to the previously created mesh. Algor Hexagon made the 8-node brick mesh, connecting the blades and support. Algor's control software, Eagle, coordinated the changes in the geometry, the moving boundary conditions, the fluid flow analysis, and the animated visualizations to predict the airflow through the fan. Let's view the animation of the airflow over time. The flow pattern changes dramatically when a blade passes over one of the two narrow ribs. The first narrow rib stirs up turbulence, which is made worse by the second rib. The wide rib tends to smooth and straighten the airflow. Turbulence generated by the narrow ribs blocks airflow in 1/3 of the fan. So, using Algor software to optimize the design, the manufacturer could increase the flow rate, reduce the power requirements, or make a smaller fan. This historic oil can was made by the Pittsburgh Manufacturing Company. I will use it to show the principle of snap-through buckling and how Algor's Accupak nonlinear software can readily analyze and predict this effect. Let's take a closer look at the oil can. Note, as I press on the bottom of the can, the movement seems linear at first. But as I press harder, there's a sudden snap, and a relatively large displacement occurs in a sudden jump. Then, when I release the pressure, it suddenly snaps back. To determine the thickness of the bottom, we purchased 2 identical oil cans and cut out the bottom of one. We measured the thickness at 10/1000ths of an inch, or approximately 1/4 of a millimeter. We began the analysis by building a 2D finite element model using Algor SuperDraw. The critical part was modeling the spherical shape of the bottom of the can. Note that the edges are fixed to resemble the way the bottom is attached to the real can. A force of 1 pound was applied at the center of the computer model, ramping it up over time to simulate the real action of pressing the bottom of the oil can with your thumb. The applied force curve versus time looks like this. Here is a graph of the displacement of the center node versus time. The graph is automatically generated by the software during the run. Note the sudden plunge of displacement at the moment of snap-through. And here as the bottom snaps back. The sound or pitch of the snap-through agrees with the frequency shown on the plot. It occurs at 198 cycles per second or hertz and corresponds to the note G below middle C. The pitch of the snapback is somewhat higher with a frequency of 396 hertz or the note G above middle C. Let's take a look at the animation of the results. The animation shows the actual response of the model to the input load curve. The animation is, of course, in slow motion, with the actual response taking only 1 second. Algor Accupak has the power and stability to handle snap-through buckling. It could make solving your problems a snap-through. Many FEA analysis packages cannot predict the effects of load stiffening when attempting to avoid potentially destructive responses to vibration. Load stiffening occurs when an object, such as this guitar string, is stretched to produce a specific frequency or tone. For example, as I loosen or tighten the string, its tone or natural frequencies will change. In an airplane or car, loads or forces, and therefore natural frequencies are constantly changing. Therefore, to predict the dynamic response, you must consider load stiffening. Algor offers 2 ways to predict frequencies as a result of load stiffening. The first way is with the vibration level 2 extender. First, we measure the force applied to produce this low A note, or a natural frequency of 110 cycles per second, or hertz. Multiplying the measured force with a leverage factor of 220 for the screw gives us an applied tension of 31 pounds. Then we measure and weigh the string to obtain its mass density. Also, we need to measure the cross-section area of the part of the string which will be in tension. Now we can plug the data we have gathered into the load stiffening module, which predicts the first vibration mode at 110 Hertz. The correct result. Note that the second mode is one musical octave higher at 220 Hertz, and so on up the musical scale. Accupak Nonlinear Analysis Extender is the second way to predict frequencies as a result of load stiffening. Note that when the A string is twanged, complicated waveforms appear. Notice that there appears to be waves within the wave of the string, and that the outer envelope of the mode shape itself seems to have waves. These waveforms result from the base frequency combining with the other frequencies within the string. For the Accupak analysis, we will twang the string at a typical spot which would occur during actual playing. Notice the tension force and the boundary conditions. Looking at a plot of the position of the center node versus time, we can get the base frequency by counting the peaks. Here we have approximately 11 peaks over 0.1 second, or 110 Hertz, which agrees with the previous calculation. Note the higher frequencies coming in here, and lower frequencies, or beating, showing up in the waveform envelope. Beating is often responsible for the low-frequency growling sounds you sometimes hear in airplane cabins. Plotting the node which was twanged, the higher frequencies are even more evident. Counting the largest and second largest peaks together, we get the second octave 220 Hertz, and so on up the musical scale. Finally, let's look at the visual response of the string as predicted by Accupak. It is this complicated response that causes a simple string to produce a rich tone. You need software that can predict the effect of load stiffening so that your designs can produce music to your ears.